All right, this will be EDEXCEL Chemistry for CH1, and we will be starting off with section number 1, so Principles of Chemistry, and under that we'll be doing chapter 1, States of Matter. States of matter. A pretty straightforward chapter, if I may, but we have to learn the concepts from the ground up. Now, starting off, we'll simply start off with the most basic thing that we have honestly known our entire childhoods. Then that exactly is that there are three states of matter. How many states of matter? We've got three states of matter that you have to know for your IGCSE levels. Now, let me actually introduce you to these three states of matter. I know you know what those three states of matter are, but here we go. So we have our trusty old solid, which is making a comeback. We have our wonderful liquid motion. And then, last but not least, we have to know about gases. So the three states of matter that you have to know is comprised of these three things. Now, actually, I'm going to let you in on a little weird type of a secret, if you may. You honestly kind of have a fourth state of matter, if you will. Yeah, you don't really have to know about it at IGCSE levels at all, but I'm just going to tell you for the fun of science. So that will be a state known as plasma. Okay, so a state known as plasma can actually be treated as being the fourth state of matter. Once again, I'm mentioning you don't have to know anything about this. You don't have to know anything about plasma at IGCSE levels, not at all. All right, I just wanted to mention to you as a little bit of a fun science fact. Now, scrolling down, I'm going to introduce you to these three particular states and what you should know about each state. All right, so let us focus in on this table. I'm going to make it a little bit more bigger. Right. So here, I'm going to use our trusty old this thing. Right. So first of all, you can see column 1 denotes to all the solids. And then followingly, you have liquids and then you've got gases. Now, the first thing that you have to focus in on here is the arrangement of particles being displayed. So typically exam questions will ask you to actually draw the structure of a solid, draw the structure of a liquid, draw the structure of a gas. Don't worry, when we are doing questions, topicals and exam oriented questions, I will ensure that you know what those question types are and that you know how to answer to get the most available marks in that particular question. So don't worry about that. We'll first learn the theory parts here. Right, so starting off with a solid, we have its structure pretty rigid like this. So we call the arrangement of those particles as being regular. They have a regular arrangement. So simply speaking, that's why all the solids that you know and see in your day-to-day life, everyday life, are regularly arranged. They don't really change their shape. Of course, if we like hammer or something, they do. But here, when you look at a solid will have a fixed shape due to its regular arrangement. This is quite the opposite when it comes to a liquid. Now, why exactly is that? That is because the particles of a liquid, as you can clearly see, are randomly arranged. Not as much randomly arranged as the particles of a gas, but they are more randomly arranged than of a solid, right? Then consequently, we've got gases. They are like completely randomly arranged. Gases are simply known for their random arrangement, completely randomly arranged, random motion, and all of that. Then let's just look at the movement of these particles, how exactly these particles move and behave. So starting off, we have solids that state that solids vibrate about a fixed position. Solids vibrate about a fixed position. What exactly does that mean? Now I'm going to consider this particle right over here. Okay, so can this guy move anywhere? I don't think so. He's fixed, he's locked in place. So the only form of movement that this guy will show is he would just vibrate exactly where he is. Okay, he's trying to move, but he can't move. So we simply call that the particle simply vibrates about that fixed position. So this particle simply vibrates about a fixed position. Very important, vibrate about a fixed position. It's not moving anywhere. And liquids, of course, you know, liquids have the liberty to move around each other. That's why they take the shape of the container. That's why they take the shape of the container. They can move. And gases, obviously, they can move in all directions. In all directions. Now, here you see the movement of gas particles is described as it moves quickly in all directions. Honestly, in chemistry, we call this a specific thing. So when a gas actually moves very quickly in all directions, we simply say that the gas shows random motion. What? The gas shows random motion. We call it random motion of gaseous particles. Every single gas you know will literally exhibit random motion. Okay, simply they randomly move apart every single place. And then what about the final thing? Honestly, this is like a simple thing. The closeness of particles. You can obviously see solids are going to be very close. Liquids are partially close. Gaseous particles are completely apart. Now, along the line of that, there is something that I actually excluded from this table because I wanted to focus on it more than these three things. And that is the energy of particles. That is the energy of particles. The energy. What do I mean by the energy of particles? Simply speaking, if you were to consider one of these particles from each state, we will be talking about how much energy they have. So simply speaking, in your perspective, in the human perspective, if we have a lot of energy, we can move around really well, right? That's a simple thing, right? If we have a lot of energy, we can move around really well. Same thing here, it's science, no? So here, solids, they can't move around, can they, that much? So the energy of a solid particle will be described as being low. Described as being low. What about liquids? We can say that liquids have moderate amounts of energy. Liquids have moderate amounts of energy, and obviously gases will have the highest amount of energy possible. That's why they move around so much. So simply summarizing, we can say that we talked about first the diagram that we can draw. Then we focused in on the arrangement of particles and then how those particles move, how close or far apart they are, and then the sixth one is perhaps the most important one, the energy of particles. All 6 points mentioned are pretty straightforward to wrap your head around. So these will simply be the states of matter, the three states of matter, and the properties of them that you have to know. Right. Continuing on, we would have to focus on how these state changes occur. How exactly state changes occur. So simply your subtopic would be changing states. Call it changing states. So under changing states, what we have to focus in on is how one state of matter can be converted onto the next state. Onto the next state. So simply speaking, as we already know, one state of matter can be interconverted into the other, right? Otherwise, chemistry wouldn't really work. So one state of matter can be interconverted into another. Interconverted into another. All right. It can be converted into another. Now, there's something interesting you have to understand when it comes to this. Okay, so this might be the first newest concept that you introduced to in your IGCSE levels. So that simply will be a concept known as this. So simply enter intermolecular forces. Enter intermolecular forces. Weird, I know. Let's hold on. So starting off with the first state of matter, I'm going to draw a small solid here. Not that much, a small solid. Boom. Okay. Then I'm going to draw a liquid. Now you should be able to absolutely do this on your own. So liquids, and then we have gases, which are highly, highly far apart. Like, okay. So simply speaking, very briefly put, intermolecular forces are simply the forces of attraction. So simply the forces among these molecules. Among these molecules. So if I were to just focus in on here, I can simply say that. What do you say about solids? Solids have very strong intermolecular forces, IF for short. Solids have very high or very strong intermolecular forces. It's literally in the word. You see it, see? Intermolecular forces. Intermolecular forces. Now, there is this concept between intermolecular and intramolecular forces as well. This, I wanted to mention this to ensure that you won't really like confuse too many things, but completely forget about that for your IGCSEs. All right. The only thing you have to know is intermolecular forces. Okay, other things we can focus on in our later, advanced subsidiary levels, our A levels, and further beyond. For your IGCSEs, what you have to know is about intermolecular forces. What about liquids? Obviously, we can say that they have moderate intermolecular forces, followed by gases having very weak intermolecular forces. That's why they can float around. That's why solids can't. Intermolecular forces. Okay, so simply put, stronger our forces, more energy will be required to break them, or to, I'll say, to weaken them. So you need more energy to weaken them. You need a lot of energy to weaken them and to move them apart. Now, if you don't understand everything about intermolecular forces, not to worry, I've not taught you everything. So we'll do this concept and then really grasp everything about it. So simply speaking, stronger the forces, the more energy that is required to break those forces. So you need a lot of energy to break those forces. So it looks something like this. So you simply have to provide heat energy. You simply have to, you simply have to provide a lot of heat energy. What do you have to provide? You have to provide heat energy. Now, as being a IGCSE chemistry student, I would not really like that you say heat energy. I would prefer if you use the term thermal energy. What term? Thermal energy. Now, heat energy is completely fine. You'll get your marks. Examiners will mark it as being right. But to add that little bit of thrill to your education, to how you handle the subject, I would suggest that you use the terminology thermal energy wherever you want to say heat energy. Okay, heat energy and thermal energy, they're literally the same thing. Thermal is actually the scientific term for heat. So what will you say for heat energy from this point moving forward? Thermal energy. You'll call heat energy thermal energy. All right, you will simply call heat energy thermal energy. Right, so simply speaking, if you want to separate these particles for solids, you need to provide a lot of heat energy. How much? You need to provide a lot of heat energy. You need to provide a lot of heat energy. For liquids, you don't have to provide as much to convert them into gases. Don't worry, I haven't mentioned anything about interconversions yet. We'll get to that. And then for gases, you honestly don't need to provide even a little bit more. It's just a little bit of, no, honestly, there's not really a state that you can go after this, so it's fine. So recap, what are we talking about? We're talking about intermolecular forces. We're talking about intermolecular forces. Solids will have very strong intermolecular forces, liquids will have moderate, followed by gases having the weakest intermolecular forces. So if you want to separate a solid, you have to give it a lot of heat energy. No, nope, we no longer say heat energy, we say thermal energy. If you want to break a solid apart, you need to give it a lot of thermal energy. If you want to break a liquid apart into a gas, you need to provide a moderate amount of thermal energy. So just like that, only interconversions are possible. Okay, so honestly, there's not really a state to go after gases, no. So typically, you won't really be asked, or you won't really talk about breaking gases apart. Okay, so not in syllabus, right? Okay, now we'll get to the actual changing state. Well, let me pick a good color. Right, I believe that's good. Yeah, okay. So now we are at the actual changing state thing that we have to be at. So changing state. The first thing that I want to mention to you about changing state is that state changes are physical changes. What? State changes are physical changes. State changes are physical changes. They are not chemical changes. They are not at all chemical changes. Not at all chemical changes. Okay? What in the world is the difference between a physical change and a chemical change? That will be discussed more in depth in further chapters, but for now, all you have to know is physical changes can be reversed. Example, you can melt ice, right? And then you can freeze the water back into ice as well, just like that. But chemical changes, now the best example that I'm going to give you for chemical changes is making an omelette. This has been my favorite example since I can remember. Making an omelette. If you crack the egg and if you cook the egg, you can't really get the egg back, right? No matter what you do, it's cooked, it's chemically changed, it's irreversibly changed, okay? Physical changes are quite the opposite. You can reverse them. Now, we'll be looking at those things right now in a little bit more detail. Right, so I'm not going to really bring in a like a diagram because I want to take my time in explaining this to you. So first of all, what's our first state? We call that solids. Okay, our first state is a solid. And then we have our liquid. And then finally, we have our gases. Okay, these are the three states that you have to know about. And then how would we go about converting from one to another? It's like this. When you convert a solid into a liquid. So I'm going to label these two in case. Solid, liquid, and then we have our gases. So when you're going from a solid onto a liquid, we call this process, it's a pretty straightforward process. Always think of simply ice. So if you were to go from ice to water, we call this melting. We call this melting. This process is known as being melting. All right, wrap your head around that. Melting. So simply melting ice, think of melting ice. Yeah. Then once we have the liquid and when we convert it into a gas, we call this process. Now here's the important thing. This is often a very overlooked process. What do I mean by a very overlooked process? Because students really tend to use a lot of words. Some say evaporation, some say vaporization, some say boiling, some even say other things. Now here, whenever I am teaching you concepts, I will always abide by the syllabus and scientific facts, okay? I'm not going to be perfect. I'm not saying that I'm going to be perfect, but you'll always be learning the proper thing in the way that your syllabus requires you to know, okay? So here, I'm going to give you the proper terminology. Throughout the entire syllabus, I'll be using the proper terminology, so you don't have to worry about getting confused or anything like that. I'm not saying I'll be 100% perfect. If I make a mistake, I will point myself out. Don't worry about that. So here, what I want to really emphasize on was that this process of converting a liquid into a gas is known as boiling. Okay, not evaporation, not vaporization. This is known as boiling. Evaporation, vaporization, boiling, they are simply three different terms. Now, technically speaking, boiling and vaporization can kind of be said to be similar, but they have a slight difference as well. So here the term you'll be using is boiling. Okay, at boiling. And one more thing that I wanted to add to this is this. So let me pick, where's my green color? Right. So here I just wanted to let you know that melting happens at the melting point. Melting happens at the melting point. Simply, that is simply the temperature. Okay, that is simply the temperature. Don't think of it too much. I just wanted to mention to you that melting will happen at the melting point. Similarly, boiling will simply happen at the boiling point. At the boiling point. Simply happen at the boiling point. Okay, right then, without further ado, I'll tell you what the reverse processes are. So now remember how I told you it's just a physical change and things can be reversed as much as you like. Simply speaking, you can go from a gas onto a liquid, and we call this process condensation. We call this process condensation. What do we call it? Condensation. Nice word. Condensation. Okay. So this is exactly what happens when it rains. The water vapor condenses back into a liquid. And then what's this process? You obviously know melting. What's the reverse of that? That's going to be freezing. Always think of ice, you know. Melting ice, freezing ice, state changes. Okay? These are the main things, the main four processes or the main four state changes that you have to know. All right? Aside from them, there are two special processes that I'm going to point out to you. There are two more special processes that I will right now point out to you. What in the world are these special processes? Now, there are very few instances, very interesting instances, where you can actually go straight away from a solid onto a gas by skipping the liquid state. Now, typically, if you want to go from a solid to a gas, you have to go first be a liquid, then be a gas. No, but there are special instances where you can go straight away from a solid into a gas. And this process has a very nice name as well. We call this sublimation. We call this sublimation. What do you call it? Sublimation. And actually, the reverse is possible as well. You can go straight from a gas back into a solid as well, and you call this desublimation, right? Those 2 points will be very easy to keep in your mind. We call this desublimation. What do you call this? We call this desublimation. Call this desublimation. Sublimation and desublimation. All right, now you can simply picture some examples for melting in your head, ice and all of that stuff, but I don't really think you can really think of an example for exactly is sublimation. Now we talked about what sublimation is. Sublimation can be seen in these things. Camper balls. What in the world are camper balls? So simply it's this, like, this white little ball that will like straight away convert into a gas. Like we typically, to keep away insects, we use this thing known as camper balls. Call this camper balls. Wait, hold on. Actually, let me show you camper balls. Right, where's my diagram? Okay, here. So simply speaking, camper balls are, these things. Yeah, you might have seen them. Typically, to keep insects away, we use these things. Honestly, iodine is a much more chemistry based example, but we don't have to get into examples that deep yet. Simply, camper balls show this property known as sublimation. Okay, so 4 main stages that you have to know: melting, boiling, condensation, freezing. 2 special things: sublimation and desublimation, and that is everything that you have to know for state changes. Next, we have to simply focus on like some simple investigation. You don't have to carry out any investigations. Don't freak out or anything like that. We simply have to talk about a couple of investigations. Now, what will we exactly be investigating about? We'll see. So, investigating simple diffusion experiments. Investigating simple diffusion. Don't freak out. I'll let you know what simple diffusion is. Investigating simple diffusion experiments of chemistry. Right? Now, what are simple diffusion experiments? Simple diffusion is when simply things diffuse. I know that's not helping at all because you have no idea what diffusion is. It's like this. Let me show you. Now, these experiments, now, when we consider matter, we know that Matter is indeed now made out of small particles, and so that's what we were talking about the entire time. No? That solids are like this, they have these particles, liquids are particles like this, gases are like this, and whatnot. So these experiments actually provide evidence that matter is in fact made up of small particles. Small particles. Now, first of all, we'll be looking at some gases. Now, I'll let you know what diffusion is with these examples. So, diffusion in gases. And this is the best way you can actually observe diffusion. Diffusion, that's a D by the way. Diffusion in gases. Right, diffusion in gases is simply a concept like this. So pay attention to this nice little diagram. First of all, let's take a look at the before scenario. The before scenario. So before we can clearly see how this container, one half of it is filled with air and the other half is filled with a nice brownish, so orange brownish gas. We call that gas bromine. The gas is known as bromine. Okay, so we filled one half of it like this and then the other half of it like this. So then we just kept this out for some time. We kept this container out for some time. And then after that particular time has actually like passed by, when we look at the container, this is what we see. Do you see how that bromine gas has gone to the other side? Simply, without any forces, there's no one telling them to go, there's no wind inside it, there's no other forces acting, nothing like that. They had simply just, what has happened? They have simply spread. They have simply spread. They have simply spread themselves onto the other half of the container. This is the concept of simple diffusion. This is the simple concept of simple diffusion. Simply this movement that they randomly do on their own, that is known as diffusion. That is known as diffusion, right? Also remember how we mentioned that gases will move wherever they want. So now you can say that gases will diffuse wherever they want. Gases will simply diffuse wherever they want. Now, honestly speaking, gases aren't the only things that diffuse. You can observe diffusion in liquids as well. So let's see how. Diffusion in liquids. Diffusion in liquids is even more interesting than diffusion in gases. Let's see why. So first of all, let's look at the before type of diagram. Right. Nothing fancy, it's not hard at all. Let's see. So blue represents a water molecule and the purple color thing is something known as potassium manganate. Okay, all you have to know about potassium manganate is that it is purple in color. Okay, so that we can actually see a color difference. That's all. You don't have to know anything about potassium manganate. Okay, right. So here's our beaker of water and then we've put some potassium manganate crystals over here. Okay, we have put some potassium manganate crystals nice and low in the beaker. And we do the same thing. We allow some time to pass. We simply allow some time to pass. And then when we come back to this container, this is what we'll observe. This is what we shall observe. What have we observed? The water is now a completely different color. Water is now light purple. Why? Because these potassium manganate crystals have, what's the word? The potassium manganate crystals have diffused through the solution. the potassium manganate crystals have diffused through the solution just like this. So after 4 hours actually. Do you see? The concentration of particles are now evenly spread throughout the solution. Evenly spread throughout the solution. You don't have to worry about these terminology that much, concentration of particles and blah blah blah. Nothing like that. Simply the particles have spread throughout the solution. What's a better word now? The particles have diffused throughout the solution. In gases, the exact same thing happened. The particles just moved, they randomly simply move from one place to another. Typically, if you have a keen eye, you would have noticed that the particles tend to move from a place where they are very, very crowded into free space. And now everything's balanced, kind of. Do you see? Here the potassium manganate, they were very, very, very crowded in this particular location. So then they simply decided to move throughout the entire thing. They simply decided to move throughout the entire thing. Right? That is the concept of diffusion. Diffusion. Right? Pretty straightforward, pretty simple. You'll see the type of questions that you'll be asked on this. Nothing to worry about, nothing too fancy. Enter. This is going to be interesting. Now we'll be making solutions, huh? You might ask. Yes, but yeah. Making solutions, what you have to focus in on is the terminology associated. Terminology associated with making solutions. Now, the word terminology might give you a stroke or something. I'm pretty sure not, but if you don't know what terminology means, simply we're talking about words, or more specifically, we're talking about certain terms. Certain terms. Well, let me get rid of this dancing pink dot. Oh my god. Okay, it's gone. Right. This guy too. Right. So simply we'll be talking about the words that we'll be using, or the terms that we will simply be using when we talk about solutions generally in chemistry, because obviously we'll be talking about a lot of solutions. Welcome to chemistry, right? Right, starting off, let me pick a good color. Okay, that's good, right. So here, first of all, I want you to look at this. Okay, this is your day-to-day beaker. This is your day-to-day beaker. And inside your day-to-day beaker, I'm gonna put water. I'm gonna put water. All right, I just put water. And then I'm gonna take, perhaps you might like it, you might not like it, but this is sugar. This is sugar. And I'm gonna add this sugar into this beaker as well. So now when I add it, so after some time, what exactly is going to happen? This sugar will simply dissolve, right? This sugar will simply dissolve in the solution. The sugar particles will diffuse across the entire solution and they will dissolve, right? So now here we always have to say, so when referring to the solution, we're going to always have to say, oh, water, oh, sugar, now they are mixed and blah blah blah. That's not the chemistry way of handling things. How exactly do we do that? It's like this. This water that these sugar molecules dissolved in, we call that guy the solvent. What is it? The solvent. The solvent. The sugar or the solid that simply dissolved in the solvent, we call him the solute. We call him the solute. We call him the solute. What do we call him? The solute. So when these guys mix, we get simply a sugar solution. We simply get a sugar solution. We simply got a sugar solution, nothing fancy. This is simply a sugar solution. This is simply a sugar solution, right? Solvent plus solute equals solution. Solvent plus solute equals solution. It can be any solvent. You can use water, you can use petrol, you can use, I don't know, another liquid. A solute can be anything as well. You can use sugar, you can use salt, anything. Okay, anything. Now here I want to really make sure you understand something along these lines as well. Okay, so now let's just say that. So now let's just say that I keep on adding sugar. So if I'm going to keep on adding sugar, then there will simply come a point where no more sugar will dissolve. There will come a point where no more sugar will dissolve. I'm kind of sure that you might have experienced this. So just take a glass of water, keep on adding sugar, and then there will be a time when no more sugar will dissolve. No more sugar will dissolve. So then we can say that we have a, what's the word? Saturated solution. Then we can simply say that we have a saturated solution. We simply have a saturated solution. Interesting word, I know. It's like this. So if you keep on adding sugar, like a lot of sugar, you get a saturated solution. And now what happens when sugar can no longer dissolve? What would happen when sugar can no longer dissolve? It will just start depositing at the bottom right here, right? That is because the solution is saturated. What's the word? How do you pronounce it? Saturated. That's because the solution is saturated. Okay, this sugar literally it cannot dissolve. It simply cannot dissolve. It's come to a saturated point. It's come to a saturated point. So now we have in our hands a saturated solution. We simply have a saturated solution in our hands. Alright, so just to break everything down and really make sure that nothing's confusing, and to give a small summary of everything that we learned, pay attention to this table. I'm going to run you through the table quickly. Right. So the solvent is the liquid. The solute will simply be the substance which dissolves in the liquid to form a solution. Solution is simply when solvent plus solute comes together, a solution, the mixture. And then a saturated solution is a solution like we talked about with the maximum amount of solute. Maximum amount of solute dissolved. Pay attention to the word that has been used here. Here it says that a saturated solution is a solution with the maximum concentration of solute. Why are we using this term and why aren't we just saying amount? Now, if you say amount in your exam, do you know what will happen? You'll get marks. So don't worry about it too much, okay? But in chemistry, whenever we try to say amount, so whenever we try to say how much of something, we say concentration. We say concentration of something, okay? Nothing fancy, that's it. And two terms that are just like literally very simple. If something's soluble, it will dissolve. If something is insoluble, it will not dissolve, okay? Sand, salt, things like that. This will be the summarizing table with all the terms, their meanings, and a simple example for you to follow. Right. So now, since we are simply in and under the concepts of, solutions, solubility, solvents, saturated solutions, and all those weird things, here's where a concept known as, let me pick a nice color, a concept known as solubility makes its debut. What is it? Solubility. Now, you might think solubility is very simple, and you might think solubility might be too hard. In either of those instances, you'll actually be wrong because solubility is a weird thing. Okay, it's got weird definitions. It's got a weird concept to it, but it's all the fun. So we'll be talking about it as much as we can. So very simply put, so if I were to very simply explain solubility, I would say that solubility is how much of a substance, how much of a substance will dissolve in a given volume of a liquid. Pretty straightforward, right? It's how much of a substance that will dissolve in a given volume of a liquid. Now, when we talk about all these things, what's the liquid called? We call the liquid a solvent. So what's the substance called? Solute. Simply, solubility is how much of a solute will dissolve in a solvent. Okay, just off of the top of my head for a basic example. So if you take sugar and water like we did before, we could simply say that in 100 milliliters of water, 20 grams of sugar will dissolve. Okay, don't worry about this. I'll explain this further as well as we go along right now. Right. Now, here's the tricky part about solubles. Now, I want you to really look at this canvas and pay proper attention to the canvas, because this is where students often go wrong. Okay. If you understand it in the order and the fashion I provided to your brain, you won't have any problems, not to worry. Okay. Solubility, here's the thing with solubility. Solubility is expressed in a particular way. That's it about solubility. Okay, you have to understand this way. You have to understand this way. Now, what exactly is this way? So, solubility is expressed in grams, okay, grams per 100 grams of solvent. Okay, don't try to bite your teeth or anything. I'll explain. Solubility is expressed in a particular way, and it is expressed in this grams per 100 grams of solvent thing. What in the world is that? That is exactly what we are about to learn right now. So peep this. What do I mean by peep this? I mean simply just look at this, and this is the explanation. Okay. So for example, I'm going to talk about sugar's solubility. I'm going to talk about sugar's solubility. All right, we'll be talking about sugar solubility. Don't know why I put that down. So sorry. Wait. Right. We're talking about sugar's solubility. Here's the solubility of sugar in figures. 20 grams per 100 grams of water. That is sugar's solubility. Okay, let's try to make sense of these values. Don't worry. Let's say I have a simple beaker, okay, day-to-day beaker, and I have water inside it, okay, and I have water inside it. This is our solvent. Now, how much water do I have? I have 100 milliliters. Okay, when I say 100 milliliters, it's really easy to wrap your head around this, right? Just 100 mils of what? What if I were to tell you that I have 100 grams of water? It might be weird at first, but I want you to know 100 milliliters of water is equal to 100 grams of water. Keep that assumption in your head. Okay, 100 milliliters of water is the exact same as 100 grams of water. Okay, so the 100 grams of water part is checked. Then what about sugar? So if I were to simply take 20 grams of sugar, if I were to simply take 20 grams of sugar and put it in they will dissolve. 20 grams of sugar will dissolve. Why will the 20 grams dissolve? Simply because that's the solubility of sugar. 20 grams can dissolve in 100 grams of water. Okay, so then what's the catch? So imagine if I put 21 grams. If I put 21 grams of sugar, 1 gram will not dissolve. 1 gram will not dissolve. Why? Why? That's because the maximum solubility of sugar is 20 grams per 100 grams. Is 20 grams per 100 grams of water. What does that mean? If you have 100 grams or 100 milliliters of water, or 100 milliliters of water, you can dissolve a maximum of 20 grams of sugar. You can dissolve a maximum of 20 grams of sugar. Okay, 1 gram will not dissolve. Then what would happen to that 1 gram? It will simply deposit at the bottom. Deposit at the bottom. You see, this solution is now saturated with enough sugar. It's saturated with as much sugar as possible. So if you keep on adding, it'll simply deposit at the bottom. It'll simply deposit at the bottom. So just to recap, here's the most important thing you have to know. This is how solubility will be expressed. Don't worry, we'll get to this concept in a second, like in more detail as well. When we talk about solubility curves, it will become even more abundant and apparent. So you don't have to worry about it that much. But I'm going to end this with a rather intriguing note. Now it's like this. This will be the solubility of sugar at room temperature. So this is considered as the normal solubility of sugar in this example, okay? In this example, this is considered as being the normal solubility of sugar at room temperature. At room temperature. Now I'm going to tell you that this solubility, now here's the thing, this solubility that we were talking about so much, it can actually be altered. You can actually increase this solubility. How? How can you actually go about increasing solubility? you can increase the temperature. You can increase the temperature. Can increase the temperature. If you increase the temperature, solubility will go up. Now, why does that happen? That is beyond the scope of this chapter. When we talk about particles, kinetic energy, and the kinetic energy theorem, we'll get to that. Okay? So for now, you don't really have to think of it too much. What I just want you to know is that solubility can actually be increased as you increase temperature. As you increase temperature. All right. This will become more abundant in a second, but this is what I want you to know. So actually, if you were to increase the temperature like a lot, you can perhaps make the solubility of sugar like 40 grams per 100 grams of water, something like that. Okay, solubility is increased, obviously, right? So to really focus in on this, I'm gonna give you this. Enter solubility curves. What? Solubility curves. Now, if you hadn't already guessed, solubility curves simply represent or talk about solubility. Okay, solubility curves. Whoops, solubility curves represent the solubility of a solid in 100 grams of water. In 100 grams of water against temperature. Don't worry, I'll explain this entire bullet point to you. Let's drag that out, right. So let me show you what a solubility curve looks like. This is your typical solubility curve. It's not complicated at all. It is not complicated at all. Okay, so don't worry about looking at this and being overwhelmed and anything in between. This is such a straightforward concept. Okay, so simply what do solubility curves represent? We just talked about this. So they will represent the solubility of a certain solid in 100 grams of water against the temperature. Okay, let's see. On the y-axis, okay, first of all, let's look at the x-axis. So simply speaking, the below axis will always be the x and this will be the y. Okay. Here we have temperature. Like mentioned that solubility curves will be the solubility against temperature. Okay, that's all you have to think about, honestly. Solubility curves will show you the solubility against temperature. You know that in any graph, we have to plot something. So it's like this. We have to plot something across something, right? Something against something. That is simply that concept, okay? Solubility against the temperature in this case. Solubility against the temperature in this case. So let's just see on the y-axis, we've got the solubility. How is solubility expressed? Do you remember? In grams per 100 grams of solvent. In this case, in grams per 100 grams of water. In grams per 100 grams of water. Okay, simply that. And then we've got the temperature. Can you see for lead nitrate and potassium nitrate, as you increase the temperature, solubility increases as well. Can you see the lines going up? Solubility increases as well. For sodium chloride, however, do you see? For sodium chloride, solubility is ideally the same. Solubility ideally looks to be the same no matter the increase in temperature. None of these things you have to memorize. You will always be provided solubility curves. You just have to know how to read those curves. So I'm just going to give you a very simple sample question. We will be focusing on a lot of these questions when we're attempting questions, so you don't have to worry about that. A very simple question I might ask you is, so how much potassium nitrate, okay, that's potassium, so how much potassium nitrate will dissolve in 20 grams of water. Okay, will dissolve in 20 grams of water at 50 degrees Celsius question mark. That's the question. Yeah, I want you to take a second and try this. It's very simple, but it might be tricky. Actually, it might be tricky. It's very simple. I want you to give this a try. And then I'll explain exactly how you are about to do this, how you should be attempting this. All right, let's see. So now what you have to focus on is potassium nitrate. Not this, but the pink line over here, potassium nitrate. What's the temperature? 50 degrees Celsius, right here. So let's trace that up. Whoops, that's the worst tracing I've ever done. Sorry. Right, so tracing things up, boom, right here. So then we have a reading of, I'll just simply say like it's near 65, we would say, because it's 60, here 70. So we'll just presume it's 65. Okay, so now we found out that the solubility at 50 degrees Celsius. Remember, it's very important to know about the temperature, because why? Solubility can differ according to the temperature. Okay, we have to talk about 50 degrees Celsius. We're talking about the potassium nitrate. We figured out that it's 65 grams of potassium nitrate. Let me pick the blue to represent the water. So in 100 grams of water, what should we know? We want to know how much potassium nitrate will dissolve in 20 grams. Okay, now if this is more weird, like if you can't wrap your head around it, look to the right. I'll explain. This is a simple ratio. So in 100 grams, 65 grams dissolved, right? We got that from the graph. Simply we need to know how much would dissolve in 20 grams. Simple, very simple grade 6 ratios. We simply want to know how much will dissolve in 20 grams of water. Okay, so you know how to solve ratios, simple mathematics. When you do this, this will be what you get. Okay, so it will be x into 100. So I'll do that for you as well. You simply cross multiply. We call this cross multiplication. You simply cross multiply. So that would become 100x when I multiply them is equal to 65 into 20. 65 into 20 should give you 0, 1, 3, 13, 1300. This should be right. This should give you 1300 or 1300, 1300. So to find x, you simply divide both sides by 100. Why do we do that? Because 100 to 100 cancels, and then it's just x, and then here you can just do simple division. X is equal to 13 grams. X is equal to 13 grams. What is this answer? So this is the answer for this. So we'll just write a simple conclusion to make sure we really understood. So 13 grams of potassium nitrate. Don't worry about the symbols, don't worry. 13 grams of potassium nitrate, KNO3. I just wrote it for simplicity. So 13 grams of potassium nitrate will dissolve in 20 grams of water or 20 milliliters of water. If you can't wrap your head around the grams of water, always think milliliters, all right? So 13 grams of potassium nitrate will dissolve in 20 grams of water at 50 degrees Celsius. We're talking about 50 degrees. At 50 degrees Celsius. At 50 degrees Celsius. With that, we have come to the end of solubility. Here we talked about solubility curves, and let me give you a little bit of good news. That is in fact the end of chapter 1, states of matter. States of matter. Now I want to tell you that Questions under solubility curves can be given in many different varieties and ways. Okay, we have to focus on those ways in which we can answer those different questions when we are actually doing questions. Step one is always theory. You have all the theory that you require for this entire chapter explained in this particular lecture. Alright, we're going to first of all solidify our theory, and then we can simply focus on the questions and how to attempt them. With that, let me tell you that Chapter 1, IGCSE Chemistry, States of Matter, under Section 1, Principles of Chemistry, is now officially over. It's now officially